Hello everyone, welcome back to another video for the series. I'm Inoki and today I would like to share a very famous concept in Olympiad mathematics. It's also really famous, I think, in junior Olympiads too. So I would like to share about it. It's called Simpson's line, and the whole point of making this video is to prove the existence of Simpson's line. But before proving the existence of it, I would like to share what Simpson's line is. So let there be a triangle ABC. Like this. So it's triangle. Okay. It's quite. No, I cannot rotate it. Okay. So we have triangle ABC. And let there be a point P. But before that, let me quickly. It's very tricky, especially if the drawing is quite big. No. Wait, I think I found the perfect line. Okay. Oh. I'm starting to see the shape. Okay, now I just need to erase some of the dirty lines to make it look a little more like a circle. Okay, so continuing, we have a nice circle, but I want it to be quite thin because I want to share a point P that is actually on the circle. I don't know why, but this is oddly satisfying. Oh, nice. I think it's not bad. Okay, so here, let's say that point P is here. And you're going to draw a normal line like this. Maybe I'll just this. Let's say that this is X, A, B, B, C. So Y, Z should be here somewhere, so we need to extend it actually like this. This seems tangent enough, normal enough. X, Y, Z. Now points X, Y, Z are collinear, meaning they form a line like this. Yeah. So, I think it would be good to just write them. Yes. So, let Simpson's Simpson's line. Let, maybe I will use parentheses. Let P be a point. Let P be a point, and let there be a point P and triangle A. Let there be a point P and triangle ABC on the same plane. Define x points x, y, z. Define points x, y, z to be the intersections, define points x, y, z as the intersections of the foots from P to AB. It should be line BC and oh my goodness, BC and CA respectively. I need to move my drawing right here, maybe here. Then if point P is on the this is called in circle and this is called circle. Oh my goodness. Circle of triangle. Sorry. Let me fix that. Point P is okay. On the circumcircle of triangle ABC. ABC if and only if x, y, z are collinear. Yes. Wait, I need to read the definition again. Oh, okay. I need to define it. Then the line that passes through XYZ are called the Simpson's line. Okay, so oh no. Let me quickly check if that finishing. Let there be a point P and triangle ABC on the same plane. Define point X, Y, Z as the intersections of the foots from P to AB, BC, and CA respectively. Line AB, BC, and CA. Point P is on the circumcircle of ABC if and only if the X, Y, Z are collinear. Then the line that passes through X, Y, Z are called Simpson's line. So what we're going to prove here, this is a definition of Simpson's line and and what we're going to prove here is the fact that the point P is on the circumcircle of triangle ABC if and only if the points X, Y, Z are collinear. So that's the statement that we're going to prove right now. So it all starts with like this. So we know that these are all right angles, and let's prove of the existence. Is this how I spell existence? It's A, right? Existence. Oh, existence. Let me try that again. I think it's A. Existence. Anyways, proof of the existence of Simpson line. So let me quickly copy our diagram here. And yep. Okay. We're gonna write a long expression. So let's prove the if condition. So first one, if point P is on the circumcircle of triangle ABC. If point P is on the circumcircle of triangle ABC, then X, Y, then X, Y, Z are collinear. So let's prove this first. Okay, so we're first assuming that the point P is on the circumcircle of triangle ABC. That means, how should we start? No, I actually know the proof, but so we can start by so notice that angle PYC equals angle PZC equals 90 degrees. Therefore, PYCZ is cyclic. And now we're going to use this information right here. So first of all, because we know that this thing is cyclic, I think we can start using some of our intuitions. So we're going to chase some angles here. So let's say that here is alpha, maybe theta. Then we know that this is 90 minus theta. Let angle YPC equals theta. Then we know that angle BAC, wait. Angle YZC is also theta. Yeah, this is true. Now this is theta. This is 90 minus theta. But before we do that, let's chase some other angles, because I remember using this angle too, but I think that will maybe block something. So this is 90 minus theta, and what else is 90 minus theta? Okay, what can we use here? We know that this is cyclic, so we know that this is also 90 minus theta. And naturally this is equal to theta, because this one and this one. Okay. Yeah, so here what we want to prove here is, the thing that we want to prove here is the fact that ACX is equal to ZCY or ACY. I mean XAC is XZC. The angle XZC is equal to angle YZC. That means we know that this is collinear. So that's what we want to prove right now. So we have XZC equals theta. Wait. Theta, 90 minus theta. We don't know if this is 90 minus theta yet. Just because we don't know that the red one is collinear. I mean, it's a straight line. We don't know that yet. Then how should we continue? We don't know if these 3 points are collinear yet. Then based on what we know, because this whole thing is cyclic, we also know that. Okay, so let's start writing. Notice that angle PCY equals 90 minus theta, and this is also equal to PCB, angle PCB. Now this is equal to angle PCB, and this information here is quite useful because we know that the angle, point P is on the circumcircle of the triangle ABC, which means this is equal to angle PCB is equal to PAB, and this is equal to angle PAX. We know that this is equal to angle PAX. So angle PAX is 90 minus theta. That's one thing that we know. That means this one is theta. But not sure if that's quite useful here. So let's draw them real quick. So we know that, so far we know that PAX, this is 90 minus theta, which means because this is 90 degree, we know that this angle right here is theta. And because we know that this angle right here is theta, what else can we try? What else do we know here? Wait, we know that PZAX, did I say PY? No, it's it's PZ. I used the wrong angle. Angle PZA equals angle PXA equals 90 degrees. That means PZAX is cyclic. Okay, we know that is true. Now, that means we know that this angle right here, because let me change the order. So sorry about that. Therefore, angle, which one is it? This is cyclic, so angle, this one and this one, right? XZA equals, do we have YAC here? No, we don't have YZC here yet, right? No, we don't have YZC here yet. We just now need to prove that this is also equal to theta. We know that this angle is also theta, but how do we prove that? So we XZA is theta, so we just need to prove that, like, YZA. Do we have YZA here, or like AZY? No. Or like CZA. I mean CZY. Oh, we have P. I'm not sure if that's that useful here. Wait, I think we need to use here we go. I found it. So, yes, I found it. Moreover, what we had like in the beginning was correct. So, moreover, my memory just slipped. Moreover, angle YPC. No. PYC. PYC equals angle PZC equals 90 degrees. Therefore, no, this is the wrong spelling. Moreover, therefore, quadrilateral PYCZ is cyclic. Because this thing is cyclic, we know that. Thus, this thing is cyclic, which means this one, this angle right here is equal to this angle right here. We're not thinking about x here. So YZ is a line here. This one is equal to this angle. Thus, angle YPC equals angle YZC cos theta. Because angle XZA equals angle YZC equals theta, X, Y, Z are collinear. Yes, we finished our first half of our proof. And the reason why like if XZA is theta, YZC is theta, then X, Y, Z are collinear. And the reason why that's true is because we know that ZA and ZC are the same line. So basically for angle XZA to equal YZC, which is also equal to YZA, because we know that ZA and ZC are the same, the line ZA and line ZC are the same. For them to be equal to each other, we must have then collinear, or else the angle will be different. That's the only chance. Let's prove our second part. Line if x, y, z are collinear, then point P lies on the circle of triangle ABC. This is correct. Yeah. So the proof is quite simple here, and that's because, let me copy our diagram. Let's work in reverse. So if x, y, z are collinear, we have so let angle YZA, YZC equals angle XZA equals theta. And again, ZA, ZC, their line ZC are the same line by construction. Then we know that we know that because I'll just write them. PCC equals 90 degree. YCZ is cyclic. Thus, angle YPC equals theta. We know that this is theta, and wait, if this is theta, we just now need to prove for P to be no, but how do we prove that P similarly quadrilateral, similarly, I just can't pronounce those words. Similarly, because what's that? Angle PXA equals angle PZA equals 90 degrees. Quadrilateral PXAZ is cyclic. Thus, angle XPA equals theta. Now, how do we complete our proof from here? For us to prove the P theta, and we are going to continue. So YPC equals theta. So angle PCY equals 90 minus theta. Similarly, we have angle PAX equals 90 minus theta, because angle PCY equals angle PAX equals 90 minus theta. Oh wait, PXY is equal to, angle PCY equals angle PCB equals 90 minus theta. And that's because we know that YC and BC is the same. They are the same line. YC line and BC are the same line by construction, and we have angle PAX, and that is also equal to angle PAB by construction. Therefore, PCB equals angle PAB. Is this right? PCB, PAB. And for this to happen, P must lie on the circle, because this is also an if and only condition. If and only if condition. Yeah, it is indeed the if and only if condition. So therefore, point P lies on the circle of triangle ABC. And that completes our proof. Nice. Yes. This was a video about Simpson's line, and maybe tomorrow I might make a video about a problem related to it. Then thank you so much for watching this video, and see you tomorrow. Thank you so much for watching this video, and see you tomorrow. Thank you and bye.